Now, uniform time warping is nice, together with all that scaling and blah, 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 to compare time series that have different length and different baselines, different amplitude scales and stuff like that, but you still want to compare them according to their shape. But what if this shape is just, as I just mentioned before, is just shifted in one of the time series a little bit along the time axis? You cannot account for that because you're still comparing after doing that upsampling and the scaling and the shifting. You still compare each time slot with each other. What can you do if you have some of these slight distortions, slight shifting along the time axis, not along the amplitude spectrum? Well, then you need dynamic time warping. You have to do the time warp. You have to go back and forth in time. Whoa, sounds fascinating. And that's what it is. So here is dynamic time warping. So the idea is that you allow at least local stretching, a local stretching of one of the two time series in order to minimize the distance between them. Yeah? So you allow also comparisons of time series, of course, with different length, but the most important point is that now if the time series have somehow comparable shapes, yeah, but a little bit distorted, a little bit shifted now along the time axis, not only along the amplitude spectrum, but also along the time axis, you want to account for that by just allowing a local stretching of one of the two time series, or of both time series, basically. Yeah? And there are tons of possible applications, like the comparisons of hummed songs, where the timing maybe is not the perfect in both cases, handwritten documents, biometric data and stuff like that, where you have some sort of distortions, shiftings along the time axis. Yeah? And here you see the comparison, at least on the idea level, between Euclidean distance, where you compare the red and the blue one time series here, one by one, by just comparing each time slot with each other. And with dynamic time warping, you can do the time warp, so you can stretch or make a virtual stretch of the red one. So everything here will be mapped. All those time slots here from the red one will be mapped on this time slot from the blue one, and the second time slot from the blue one will be mapped to maybe this or this time slot here, and then to this time slot here, and so on and so on. Yeah, so you allow for some kind of stretching, one of the two or both actually, to find the perfect match between the values of the two things. Yeah, and the definition here looks a little bit mathy, but if you consider it or just metabolize it, you will see that it pretty much looks like what we already had with the edit distance. Yeah? And it's basically an edit distance on time series. But let's have a look. So you have two different time series, may have different length here, x and y, and you need also a ground distance, okay, whatever that is. And now the dynamic time warping distance is again a recursive function. So the base case here is that both are actually empty. Both argument time series have length 0. Then the dynamic time warping distance is 0. Now we are looking for distance, by the way, not for the number of edit distance, which is the edit distance. Not the number of edit distance here, but we want to compare the elements here. Yeah. So if there are no elements to compare with, we have a distance of 0. Then the other baselines here is, well, if you have a sequence X and you compare it to some empty distance, some empty sequence, it's the distance is infinity. Yeah, and the same holds true for the other way around. So those are the base cases, and now the interesting recursive case is that you look to match, or you match the last elements of both time series, the last element of x and the last element of y, with your specific ground distance, and take that one here plus the minimum. And now it's interesting. Well, we have again three cases, like in the edit distance case. Yeah, you can stretch nothing, so you compare the last elements of x and the last element of y, and then take the last element of the remaining or the prefix of x and the prefix of y. So there is no stretching in both cases. Or you can stretch x by just holding x as it is and looking for the prefix of y. Or you can stretch y by looking at the prefix of x and hold on at the last position of y. Yeah? And of course, in all those three cases, you get something, and you take the minimum out of that. So time series are typically real valued, so the absolute distance is often used as a ground distance. So the Manhattan distance, like this one here, is just used here for the ground distance. So the ground distance is very often just last x minus last y in Betrag, absolute value, and then plus the minimum of the recursive calls. And the most prominent variant of dynamic time warping is Manhattan distance as a ground distance, as just explained here. And for P, we use 2, so we take the Manhattan distance as ground distance to the power of 2 plus this one here. Okay, which is basically something like the Euclidean distance somehow. But not now the Euclidean distance, because we are now allowing for time warping, which is down here for this stretching along the time axis. Now, as I told you before, dynamic time warping is more or less the same as the added distance. So it also computes an optimal alignment. Dynamic time warping computes an optimal alignment between two time series. And that alignment can be represented, in that case it's called a warping path. Sorry, not a wrapping path, a warping path. This path here is shown here, P1 to PL, and the elements of this warping path are just the elements of the two corresponding time series x and y that are compared at the particular time point or at the particular index of the warping path. The first index here will go from 1 to n, which is the length of the first time series, of course, because those are the elements, the indices from the first index, from the first time series, and the second index goes from 1 to m, which is the length of the second one, obviously. And this warping path has to have some inherent properties. So first of all, the boundary condition says that the first entry of this warping path is the entry 1, 1, meaning that we at first compare the first element of x and the first element of y. And also the last element is clear of this alignment, because at the end we have to compare the last element of x and the last element of m. But everything in between is more or less free, first of all. Well, it's not perfectly free, because we have another three conditions here. The first one is monotonicity, meaning that if we go further from left to right, there's no movement back in time. So for example, here we have the blue thing and the green thing here, and maybe those red ones here belong to the blue time series. So since this one here is compared with this one here, the next one here from green can only be compared with this one here or with the next one in the blue, but not with the previous one in the blue. So this would be a violation of the monotonicity criterion in the blue time series, or the other way around, that would be a monotonicity fault in the green one, of course. So there is no movement back in time in this warping path here. So both of these indices can only stay where they are or move upwards, but cannot decrease actually. They can only increase or stay the same. Continuousness means that we don't have a hop greater than 1 in both indices, so there is no time slot missing. So that would be a missing match here, which is also not allowed. So this one here, which is not mapped to one of these, so the lines obviously should indicate or represent the maps, the mappings that we have. This would be not allowed here, because we have a time slot which is missing in the blue one, has no matching partner in the green one, and that is not allowed due to the continuousness property. So this alignment here would not be a proper alignment, a proper warping path in that case. And then that we have, last but not least, maybe a little bit trivial, but worth mentioning, is that the maximum is bounded of this of the length of this the length of the path of this warping path is bounded by n plus m plus 1. And we'll see why that is actually. Well, it means that, well, if we think about the matrix representation of edit distance, we can go from one corner to the other corner, and then, for example, right and then down, or down and then right. That would be the longest path, so to say. So that is the length constraint here.